All right, we're going to continue on where we left off. So pretty much last time we talked about balancing equations, and obviously a couple important things that we talked about when you balance an equation. Clearly, when you're using an equation, it should always be balanced. And the main two things are, again, that we only change the coefficients. So we never change anything else. So only the numbers that come in front. And as we talked about, when you are all said and done, all of those numbers in front do need to be whole numbers. And the second part of that is they do need to be the simplest set of whole numbers. So once again, if this was a balanced equation, we could again go through and divide everybody by 2 and still end up with whole numbers. And this would again be the properly balanced equation. And again, sometimes that happens. People can see larger numbers, and if you can again reduce down all those numbers by a common number and still hit whole numbers, then you should definitely do that. We also saw and we talked about that sometimes to balance an equation, a fraction can be used. And it's perfectly fine to use a fraction. And typically speaking, if you're going to use a fraction, the number up on top is the number you need to balance it. And the number on the bottom should match the subscript that's to the right. And you will always sort of choose to write a fraction, hopefully, in that case. Again, you do need to clear the fraction when it's all said and done, so you need to multiply everybody by the denominator, and that should then give you a balanced equation that has all whole numbers for the coefficients. The last thing we sort of talked about with balancing, again, is if you have some polyatomic ions maybe on both sides of the, maybe something like this. On both sides of the arrow. A lot of times it's much easier to kind of keep them together, balance them as whole units rather than going individually through them all. And again, usually things will sort of fall into place. Any questions on balancing equations? All right, now that we talked about sort of balancing equations, we're going to talk about types of reactions. And there's really kind of 2 big categories of reactions that we're going to talk about. And when we talk about a reaction taking place, there's really kind of 3 reasons why a reaction takes place. One of the reasons is you form a solid or a precipitate. 2 is you form water. And the third reason really why pretty much all reactions take place is there's an electron transfer, or a transfer of electrons. Now, when we talk about ways to classify reactions, as I mentioned, there's really kind of 2 big categories. One is what we did the other day there, which is double displacement reactions. And in double displacement reactions, that's basically when you have 2 ionic compounds that react with each other. And like we talked about, basically the 2 positive guys switch partners. And I'll give you 2 new ionic compounds on the other side of the arrow, like so. And underneath double displacement, as we'll talk about, are more specific ways to classify a reaction. And these are things like precipitation reactions. These are also things like acid-base reactions. And ultimately, double displacement reactions, the big category, accounts for basically reason number 1 and reason number 2 a reaction takes place, the formation of a precipitate or the formation of water. So ultimately what's happening in these double displacement reactions is either you're going to make a solid or you're going to make water. And again, that's 2 of the 3 reasons it happens. Again, there are more specific classifications that fall under there that are still double displacement reactions, but they're called something else. But ultimately, there's still a double displacement reaction that's happening. The other big classification of reactions that have many different classifications that fall under it is redox reactions. And redox reactions does mean oxidation and reduction. And what the redox reactions take care of is really reason number 3 why a reaction takes place. There is definitely some transfer of electrons that occur in a redox reaction. So pretty much all reactions will pretty much boil down to falling underneath these two big categories. And again, double displacement, solid and water being formed, and redox really takes care of electrons being sort of transferred. So we're going to start out with pretty much double displacement here and talk about those type of reactions. But before we talk about double displacement reactions, we also want to talk about how things either kind of stay together, how things break apart. And that is what is known as electrolytes. So electrolytes are substances that produce ions in solution and conduct electricity. And it really is the presence of those ions, which is the really important thing here. The presence of those ions helps everything sort of be completed. It helps to conduct electricity. Yeah.
So I'm taking physiology, and so they mentioned kind of like the same concept. Electrolytes aren't just like what we consume as well, right? There's other electrolytes for chemistry that right?
Correct. So basically, the basic definition of electrolytes is something that will basically produce ions in solution, and that could be anything from like acids to bases or electrolytes, which you probably wouldn't want to drink too much of those things, or some of them at least. So yeah, so it's a general term of things that can produce ions in solution, basically, and basically there are things that will break apart in solution. Some will completely break apart, some will partially break apart, and there's some that are non-electrolytes that obviously don't break apart, and we're going to talk about those as well. But yeah. All right, and it's like Gatorade right now. We got to replenish your electrolytes and all that good stuff, right? So let's start with strong electrolytes, and what strong electrolytes are things that basically, when they go for a swim, they will 100% break apart into ions. Now, most ionic substances are strong electrolytes. So if you had really a sodium chloride solution, in that actual sodium chloride solution, you would have basically Na plus and Cl minus. And if we put that sodium chloride solution into like a beaker, or that is a sodium chloride solution, that is pretty much all we will have in that beaker is sodium ions and chloride ions basically floating around. We will have 100% these guys floating around. We will have none of these guys still together. So you'll have none of that sort of sodium chloride unit still together. And this is a strong electrolyte. You can think of it as a one-way street. Everybody's going to dump out into ions. And because it completely breaks apart and produces a lot of ions in that solution really quick, it's a very good conductor of electricity. So there used to be experiments, or sometimes people do experiments. They'll take a light bulb, has some electrodes attached to it, and put it into some solutions. And if you put that electrode that's attached to that light bulb into a strong electrolyte solution, your light bulb will turn on and be very bright. So your light bulb will definitely be very, very bright and shiny because there's a lot of ions in that solution, and it helps conduct electricity, kind of complete the circuit, and you will definitely have that. Now, most ionic compounds and solutions are strong electrolytes. They pretty much will break apart. Strong acids are also strong electrolytes, and a listing of some strong acids, the 6 major strong acids: hydrochloric acid, nitric acid, perchloric acid, sulfuric acid, hydrobromic acid, and hydriodic acid. So that's your 6-pack of strong acids. And for example, if you had hydrochloric acid solution, it is going to completely break apart into H plus and Cl minus. And the idea there is the same. In our hydrochloric acid solution, we have basically all these ions floating around. And really what makes something an acid is the ability to produce free H plus in that solution. So since this thing, when it goes for a swim, is going to break apart, it's going to generate a lot of free H plus in that solution, and that's why it's a really strong acid, because of that ability to release that. By the way, some strong bases are also strong electrolytes. Most strong bases will have hydroxide sort of in the formula. So things like sodium hydroxide, potassium hydroxide. If you go to the periodic table and you find lithium, and then you find a little sodium, and then a little potassium, hang a right-hand turn there to group 2, calcium, strontium, and barium. Let's try to fit that in there. If you hook any of these guys up with some hydroxide that's in the actual formula, they're most likely going to be strong bases. So that's where a lot of our strong bases come from. And it's the same idea. If you dump sodium hydroxide into, or you had a solution of sodium hydroxide, it will 100% break apart into sodium ions and hydroxide ions. And again, you're going to get 100% of these guys in solution, just like up here, 100% of these guys in solution. And that's what makes it a strong base, because the definition of base is something that can produce hydroxide in solution. So it's going to produce a lot of free hydroxide really, really quickly. And again, that's why it's going to be a strong base, strong acid. All of those things are also strong electrolytes. Any questions on that? So with the strong electrolyte, we would expect it to completely just fall apart basically into ions in solution. Now, in addition to strong electrolytes, there are also weak electrolytes. And weak electrolytes are a little bit different. They actually mainly stay together, but will break apart into a few ions. So for example, if you take hydrofluoric acid, it will break apart into H plus and F minus. Now, different than hydrochloric acid, hydrofluoric acid is actually a weak acid, and it's a weak electrolyte. And when you have a solution of hydrofluoric acid, different than HCl, which completely breaks apart, in the hydrofluoric acid, you basically have the units of like HF still there together. And it will break apart a little bit into some ions, but it's going to mainly stay together. So in this case, it's going to actually mainly stay together. And we'll produce a few of these guys, a few ions in solution. And because of that, if you kind of take the same sort of example with like a light bulb that's got some electrodes, and you put it into a weak electrolyte solution, your light bulb will turn on, but it'll be very dim, almost like it's dying. So it kind of has just a little bit of juice there to semi-power up, but it's not going to be as bright as, say, a strong electrolyte solution. And that is because it has a lot fewer ions in that solution. It has more of the whole units together. We also see in this type of electrolyte different arrows. We see arrows that actually head in both directions in this case. That is different than what we see in a strong electrolyte, which is basically a one-way arrow. Everybody's dumping out to the product side in this case. Here with a two-way arrow there, that is what is known as a reversible reaction. And in a reversible reaction, there's actually two directions. There is the reactants going to products, which is referred to as the forward direction. And what happens in this type of reactions, which you'll learn all about if you take 200B, but what happens in this type of reaction is at some point, once you start making some products, those products will actually come back together and make some more reactants and kind of head in the opposite direction, going from products back to reactants. That is known what is known as the reverse direction. Eventually, this reaction will reach the basis of Chem 200B, known as chemical equilibrium. And what chemical equilibrium means, and people have a wrong idea about the name because it sounds like equal. It does not mean that you have equal amounts of everybody on both sides of the arrow. What it is actually referring to is the rate of the forward direction will eventually equal the rate of the reverse direction. So it will go to the products just as quick as the products will come back to the reactants. And what that does is not necessarily mean that you'll have equal amounts of everybody on each side of the arrow. What it does is it locks everybody into place. So whatever their concentration is at that point where the rates equal each other, they will be able to maintain those concentrations pretty much indefinitely unless you do something to screw it up. And that's what equilibrium means. Now, when we have weak electrolytes, we do use these two arrows heading in both directions to indicate that it's a reversible reaction. And I would say in most cases, most weak acids and weak bases are weak electrolytes. So some weak acids like we see here, hydrofluoric acid, nitrous acid, hydrous ionic acid. Weak bases, pretty much your most popular weak base is ammonia. And a lot of organic compounds that have nitrogen in it are actually pretty much bases. How do you know it's a weak base? Well, that's probably why it would be good to learn these for this class and your next class. These 6 strong acids are pretty much your big 6 there. And if it's not one of those 6, you could probably make a pretty safe assumption that it's going to be a weak acid. So by just process of elimination, it's not one of those, and you know it's an acid, it's probably going to be a weak acid. And those, again, are very common. What we have for weak electrolytes are very commonly these guys here. Any questions on that there? Now, the last type here is a non-electrolyte. And a non-electrolyte will still dissolve, but the important part here is it will not produce ions. So, for example, if you take sugar and you dissolve it in some water, you're going to get some dissolved sugar water, basically. Now, because sugar is carbon, hydrogen, and oxygen, that's non-metal all day, right? So that is sharing of electrons and covalently bonding. So no ions are produced here. And because there's no ions produced here, pretty much if you took your light bulb example we've been talking about and you put it into a non-electrolyte solution, it will not go off, not turn on. So non-electrolytes don't produce ions and again will not conduct electricity. So for example, water is a very bad conductor of electricity, right? If you have pure water. Obviously, water has no ions in it if it's pure water. Again, the water, by the way, coming out of your faucets are not pure water. They do have ions in it, and you will electrocute yourself if you blow dry your hair in the shower, right? But if you have pure water, it's actually a bad conductor of electricity because, again, it doesn't really have any ions that are present. They actually put ions into water to kind of clean it and stuff like that. So it definitely has ions, water that comes out of our sink. So again, safety note for anybody listening, don't blow dry your hair in the shower, right? So again, as we talked about with a non-electrolyte, here's a much better picture than what I drew. If we have a light bulb hooked up with some electrodes, again, it's not going to turn on because no ions are present and we're going to get no electricity conducting. Here's a weak electrolyte. And again, we're going to have a few ions or so produced, mainly going to stay together as whole units. But the light bulb here will turn on a little bit there. As you can see, it's a little bit dull or dim. And here's a strong electrolyte by comparison where we have pretty much all ions present. And you can see it conducts, obviously, electricity a lot better because of the presence there of those ions that are in solution. So again, here's another example of obviously our strong electrolyte, 100% ions, going to conduct electricity really well. Here's another acid, that's acetic acid. That is basically the main acid there in vinegar. And it also is a weak acid. Again, we see the arrows heading in both directions to indicate there's a forward direction and reverse direction. Once again, here for our sodium chloride, it is a one-way street. Everybody's breaking apart into ions. And again, that's if you do see an equation written like that, that is a big tell of you're dealing with something that is a weak electrolyte. Now, when ions do dissolve in water, they go through a process known as hydration. It really is a intermolecular force known as ion dipole interaction. And ion means there's an ion, a cation or an anion. Dipole we find in polar molecules like water, right? So that's where we find polar molecules. And basically what happens is if you have a positive ion and you have a negative ion, because water here, for example, is a polar molecule, that means when we look at water, there is a positive side and a negative side of water. The oxygen is more negative, the hydrogen side is more positive. So when you go take something like sodium chloride and you want to dissolve it, what happens is these water molecules will actually surround the positive ion through its oxygen, which is more negative, to help it in the dissolving process. And because water has a positive side and a negative side, that works very conveniently for our negative ion because it also gets surrounded by water, but it gets surrounded by water via the positive side or the hydrogen side. And that does two things. That is basically how your solid dissolves, badly drawn there. That is how your solid basically dissolves. It gets surrounded by a bunch of waters. And as you hopefully know, when you dissolve something like that, that is a physical change. It's not a chemical change. And you just can't see it. It does. People think it disappears. People think it some type of chemical change or reaction occurred because you can no longer see the solid when you dissolve it. But the reason you can't see it is there's a heck of a lot of water molecules around each of those ions, so you can no longer kind of visually see them being present. So the water molecules helps it dissolve. It also helps prevent this really strong attraction between this positive ion and this negative ion. And we help it dissolve, right, by usually mixing a little, right? So usually we'll mix. What that does is throws a lot of water molecules on your solid, ionic solid like sodium chloride. Also provides some energy that helps in the dissolving process. By the way, again, we know this is a physical change because perhaps you've done this, I'm pretty sure at some point, maybe in your life. If you heat this up, right, what happens is all the water molecules will start to evaporate away, right? And now there is no water molecules between those ions, and now they're going to be very happy to come back together with each other, and you will see that solid reappear as probably like a crystal. Very similar to those experiments we did in 7, right, where you kind of evaporated off the water and you're left with like a solid residue, right, and all that kind of stuff. So that's the same idea here in this case. Now, non-electrolytes, as we talked about, pretty much are really covalently bonded things, although they may be able to dissolve through some property. Again, they do not produce ions, so they will not conduct electricity. Here's just a table, kind of what we talked about. Your ionic compounds, strong acids, strong bases is going to be your strong electrolytes. Pretty much your weak acids and weak bases is going to be your weak electrolytes. And again, a lot of organic sort of guys, especially contain carbon and hydrogen, are going to be more like non-electrolytes. All right. Now that we understand sort of, things that can be strong electrolytes, weak electrolytes, and so forth, let's talk a little bit about solubility and how things dissolve. Things do dissolve in each other when they are using similar types of intermolecular forces or similar types of interactions that they use with themselves. So if you have somebody that's using a particular type of interaction that they use with themselves, like the interaction that water uses with water, which is hydrogen bonding, and you find some other thing you want to put in there that can interact in that same way, they're going to be very soluble in each other. They're going to be able to mix in each other. Now, if you find something that is using very different types of interactions, for example, water and oil. Oil uses, as we'll talk about, what's known as dispersion forces, which are these super weak type of interactions, while water is using hydrogen bonding, which is these really strong interactions. So when they come together, not much is going to happen there because over the long period of time, they do not have a way to maintain that interaction with one another. And when you see an oil spill right in the ocean and or water, right, it floats on top, right? And that's typically what happens because they cannot mix, and oil and water really doesn't mix. So when we talk about solubility, we're talking about two things mixing, and the maximum amount of solute that you could get to dissolve in a solvent at a particular temperature is what is known as the solubility. By the way, we can make a solution, and a solution is made up of two things. One is the solute, which is the smaller part of a solution, and one is the solvent, which is a larger part of a solution. So when things dissolve and they make a solution, which is a homogeneous mixture, they get the aqueous symbol, that AQ symbol there. And that is aqueous and basically means a water environment. Now, what is the difference between aqueous and liquid? They are both obviously in the liquid state, but there is a difference. And to just simply explain that difference, if you have water by itself, that is a pure substance, that is a liquid. There's nothing else mixed with it. If you take something like sodium chloride, that is a solid, that is also a pure substance. And if you mix those together, as we just talked about, you will get the salt to dissolve in the water. And that will make a sodium chloride solution. And that is the thing that gets the aqueous symbol next to it. So aqueous means it's a solution, which ultimately means it's a mixture of two things. In this example here, the smaller part of this solution would be the sodium chloride. That would be your solute. And water, which is a very common, larger part, is your solvent. Water is not the greatest solvent for everything, but it is used a lot for ionic things because it works really well. It's also used a lot for polar things because it works really well as well. Any questions on that there? Now, when we have a reaction coming together that makes a precipitate, this is what is sometimes referred to as a precipitation reaction. And a precipitation reaction is a more specific classification of a double displacement reaction. So remember that a double displacement reaction is the one that basically is the big classification. That is when we have two ionic compounds together. As we talked about earlier, they switch partners and make two new ionic compounds on the other side. And one of those ionic compounds, when they come together, will make a solid. Hence the more specific name for this type of reaction, which is known as a precipitation reaction. So a precipitation reaction is a specific classification of a double displacement reaction. They're both double displacement reactions. It's just one way of classifying it. Now, remember that one of the reasons why a reaction takes place is you form a solid. And that is pretty much what is happening in this case. So this type of reaction takes care of the idea of forming a solid. When we look at this reaction here, this is a positive guy, negative guy, positive guy, negative guy. These are two ionic compounds together. And again, this is the only type of reaction that happens in, which is double displacement reactions. This guy will come over here and switch partners. And what we end up with when it does switch partners is on the other side here, the lead will then hook up with the I, and make our PBI. And our other ions will come together. Our sodium will hook up with our nitrate and make sodium nitrate on this thing. And again, we get this double displacement. In this particular case, the PBI2, the lead-2 iodide, makes this lovely yellow solid, as you can kind of see here in this picture here. Now, let's talk about a couple things before we get into what's going on here. Let's talk about common errors that people make, which is if we have this and we know it's going to react with this, and now we want to kind of predict what we're going to get on this side of the arrow. So maybe this side of the arrow is not given to us. So one of the things that people oftentimes screw up on when they try to do this is they try to balance the equation and also write the formula at the same time. And if you do that, as I might have mentioned when we were talking about balancing equations, you most likely are going to end up with the wrong equation and it's never going to balance. So the order in which you always want to do this is get the right formulas down first and then balance the equation. So if we look at this here, you want to look at these guys as ionic compounds. And what you want to think about is this: what are the two basic ions that make this up? This is lead-2 nitrate, which means one of the ions is lead with a +2 charge. That's why it's called lead-2. And here, this is nitrate, which is NO3 minus. I am not concerned at all at this point about the 2 that's there. I just want the two basic ions that make it up. Here, this is a sodium ion, group 1, and that is our group 7 -1. Now, when I'm trying to predict what goes on the other side, now I can put my ions together correctly, hopefully. And when you put these ions together, again, you want to put them together like you're doing kind of like nomenclature, which means when I take this guy, I am ultimately putting a +2 charge together with something that has a -1 charge. And that is how we get to our proper formula here of PBI2, right? Now, when I look at the other one here, I am taking sodium, which has a +1 charge, and I am putting it together with nitrate that has a -1 charge. And that means that we will end up with here, as we see there, NaNO3. So again here, I'm not concerned about the balancing part of it. We do not end up with, like a lot of people write something like NaNO3 2 because there's a 2 on the other side and put it in parentheses and stuff like that. So you do want to make sure that you end up with the right formulas. Now you go back and balance it using coefficients. And obviously, as we can see here, we need a couple of those and also we need a couple of those. And now we're balanced. So you always want to make sure you do it in that order. People all the time end up with not the greatest things like Na2, NO3, 2, which no, right? Or Na2, Cl2, no, and stuff like that. So again, very commonly people will get these weird formulas because they're trying to balance and write the formula at the same time. So you should always, again, do formula first, then balance. Any questions on that there? All right, now that we have it there and I color coordinated everything, that's lovely. Let's talk about what is really happening though when we dump this into like a beaker, right? So when we dump this into a beaker, we have a couple of things here. We're basically, I'll put my beaker over here maybe. We're going to take lead-2 nitrate and we're going to take also sodium iodide and we're going to throw those in. Now, those are both ionic compounds, which, as we just talked about, are probably going to be strong electrolytes, which means when they go for a swim, what we end up with is some lead with some +2 floating around. We end up with some nitrate ions. We end up with some sodium ions, and we end up with some iodide ions. So we could write another equation that represents really what is happening when we kind of throw these guys together in a beaker. And this would be this guy, which is a strong electrolyte, would break apart into lead with a +2 charge. It would also be aqueous. Now, in this case, there are 2 nitrates here, so when you pop that into the solution, you actually will get 2 nitrates that form. So that 2 comes to the front here to indicate we have 2 of the nitrate ions basically floating around in the solution. So this 2 is this guy right there. Same thing with our sodium iodide here. This is going to break apart, and since we basically have 2 of them, we do have to distribute that 2 to each of the ions. So we will get 2 sodium ions that will go into solution, and we will get 2 iodide ions. And again, this is the 2 where it's coming from basically there. And that's basically what's happening here, right? We're not just throwing one of these units in there, we're basically throwing 2 of them. So we get twice the sodiums, right, and twice the iodides that are floating around. Coming to the other side, I'll try it here. Maybe I can fit it in, do a really small arrow. We're gonna get this guy, which is solid. And things that are solid will basically stay together. So things that are solid, the way they're solid is they basically stay together. Things that also stay together when you're doing this type of equation like we're doing right now, things that are solid, things that are pure liquids, things that are gases in most cases, and things that are weak electrolytes. So weak electrolytes will basically stay together. Solids, liquids, occasionally might come across a gas as well that will stay together. Now, this guy here is also going to be a strong electrolyte, which means it will break apart. So I'll just go underneath since I'm running out of room. We will get, again, 2 sodium ions and 2 nitrate ions here. And again, that's from the 2 that basically says we have 2 of those. This equation that I just wrote is basically what's happening in this solution when we dump all that in there. This is what is referred to as, we'll start with the first equation. This equation is what is known as the molecular equation. This equation is the total ionic equation. Or again, some people call it the complete ionic equation, or some people just straight up just call it ionic equation. Now, when we look at the ionic equation or the total ionic equation, there will be, again, ions that look exactly the same on both sides. So if we look here, got a couple of sodiums there, a couple of sodiums on the other side. We got a couple of nitrates over here, and also a couple of nitrates over here on the other side. These guys here that are exactly the same, and they do have to be exactly the same on opposite sides of the arrow. And if you did everything correctly, they also should have the same number in front of them. So if you see on the left there, there's 2 nitrates. On the right, there's 2 nitrates. On the left, there's 2 sodiums. On the right, there's 2 sodiums. They also should be balanced. If you get to this equation and to this part, and you got like 1 sodium on the left and like 2 on the right, something went wrong with your balancing. They should be the same. These again are what are referred to as spectator ions. And as we talked about the other day in lab, spectator ions are basically things that are just watching. They are not directly involved in what is happening in this reaction. And by the way, what is happening in this reaction is this. We're forming a solid. So those ions are not involved in the solid formation here. We could cross out those ions on both sides. And this is going to leave us the third type of equation, which is known as the net ionic equation. And that is telling us exactly in this reaction what is taking place. And that is the lead with a +2 charge is going to hook up with the iodide with a -1 charge to make this yellow solid that is lead to iodine. So basically what happens in this solution is you have all these ions floating around, and these 2 guys decide, hey, we like each other. We're going to make that yellow solid that we see over here. And they're going to come together and basically drop out a solution. Will they drop to the bottom? No, it'll probably just become cloudy and you have some yellow stuff floating around. But that yellow stuff actually is a solid and a precipitate. And what that is doing is bringing those ions out of solution. where you find ions are in solution floating around. So when you make a solid, it's like grabbing those ions and throwing them out of this pool, basically, right? And they're going to get out of the water. They'll still be floating around. Maybe you centrifuge them. They'll come down to the bottom of the test tube, and you can basically take them out as a solid. Any question on those three types of equations? So again, in the total ionic, if it's a weak electrolyte, a solid, or a liquid, occasionally a gas, you do not break them up, you keep them together. So how do we know if we are going to make a solid when we put these two ions together? And that's the solubility rules here. And the solubility rules help us decide that when we put these two ions together to make an ionic compound, would we expect a solid to form, or would we not expect a solid to form? So there's two types of outcomes from this. There are things that are soluble, which means no solid. And those are the things that get the aqueous symbol next to them. So if you determine that that thing is soluble, that is the thing that gets the AQ symbol next to it. There are things that are insoluble, and that means you will get a solid form. And those are the guys that get the solid symbol next to it, or the S. People get confused with that all the time because they think soluble, they should put the S on that. But the S here is meaning solid. So again, the S is actually for the insoluble, which makes a solid. So here are the solubility rules. What we're looking at here are things that are typically soluble in water, which means typically everybody here on the left-hand side should be soluble, should get the aqueous symbol next to them. So let's take a look at the first set of rules here. Anything basically from group 1, like your sodium, your lithium, your potassium, and ammonium. Those things are soluble. And if you look to the right-hand column, these are exceptions. And there actually are no exceptions in that. So what does that mean? That means as soon as you see any of those guys, anybody from group 1 or ammonium in a formula, you could just lay up aqueous next to it. There's no exceptions. You know it's going to be soluble. You know it's going to be a solution, so it's not going to make a solid. If you have anything that is nitrate in it or acetate, there also is no exceptions on that. So if you see nitrate in a formula, you see acetate in a formula, you could give it the aqueous symbol. It's going to be basically a solution. If you have chloride, bromide, or iodide in a formula, it is going to be soluble. The difference, though, here is when we go to the right-hand side, there are some exceptions, and there are actually 3 exceptions. Silver, mercury 1, yes, and lead 2 here, yeah. So if you have any of those things, chloride, bromide, and iodine in a formula, and there is no silver, lead, or mercury, it's going to be soluble. But if you have chloride, bromide, or iodine in a formula that is attached to either silver, mercury 1, or lead, it is actually going to be the opposite and become insoluble. So if you have any of those guys, it's going to become insoluble and be a solid, and you would expect a precipitate to form. If you have sulfate, it is soluble in everything, but there are also exceptions to that, which means if you have sulfate with silver, calcium, strontium, barium, or lead 2, it will not be soluble, but it will be insoluble, and they would get a solid. Yeah. Any questions on that there? Now, these are things that are typically soluble. There are also some things that are typically insoluble. So let's take a look at those. Maybe, there it is. So these guys on this table are typically things that are insoluble, which means everybody on the left here typically will get a solid and make a precipitate if it's there. Let's take a look at the first one, which is hydroxide. Hydroxide is typically insoluble except basically the same rule we saw in the previous table, anybody from group 1 are ammonium. So that's basically the same rule as the first rule on the last table. These guys are what are known as being slightly soluble, And slightly soluble means pretty much what it sounds like. A little bit will dissolve. But most people consider slightly soluble to be closer to insoluble than soluble. So most people sort of consider it that way. When we look at sulfide, it is going to be insoluble in everything. Once again, this is the same exception. This is our group 1 exception, our ammonium. Our calcium, strontium, and barium will be soluble. So these guys would get the aqueous symbol. These guys would get the aqueous symbol if it's on this side of the table. Lastly, carbonates and phosphates are insoluble. The only exception is group 1. The good news on the insoluble guys is most of the exceptions is the first rule on the other table, which is they're soluble in everything. So it still falls back to that same idea. If you see something in group 1, or ammonium, you're good to go with aqueous. So that is why, for example, if we took the equation that we just looked at, which was nitrate and sodium iodide, right? So we had lead to nitrate plus our sodium iodide, and that made our sodium nitrate plus our PbI2, and I feel like I need a 2 there as well. So again, how to use these rules, you want to decide, is it aqueous or not? I'm going to look at this. Although I may not see lead, I definitely see nitrate. Nitrate's right there. Nitrate is soluble in everything, no exceptions. I don't need to look any further. I know that's going to be an aqueous solution. I hit sodium right off the bat. I don't really need to go any further. There are no exceptions for sodium, which is group 1. I know it's going to be aqueous. You could also look at I. In this case, I is soluble in everything except for these 3. And obviously, in this case, that's sodium, which is not one of those 3. So it also would still be aqueous. Come on over here, I hit sodium. That's all I need to look at. It's going to be aqueous. I could also look at nitrate, which is also soluble in everything. So it'll give you the same answer. Now I look over here. I may not be able to find lead, but I find iodide, which is right here. And it's soluble in everything except for silver, mercury, and lead. And in this case, it is hooked up with lead, which means it would be on this side, and it would be a solid. So this is how you can predict whether or not, when you put these things together, if you'll get a solid or something that is aqueous. Any questions on that there? So why don't you take a moment, use solubility rules, and decide, will these... Okay, so let's take a look. So again, when we're looking at this, I see potassium there, and if we take a look, potassium's right there. There are no exceptions. So again, really, that is as far as I really need to look, and that would be aqueous. If you are soluble, I guess, to answer the question. You could also look at hydroxide in that table, which will tell you it's insoluble, except when it's hooked up with somebody from group 1, which in this case it is. So it'll tell you it would be the opposite. Here, again, may not find silver exactly, but we will find bromide. And again, bromide, if we kind of look at that table here, right there, bromide is soluble in everything except for silver, mercury, and lead. And in this particular case, I believe we got silver with it, which means instead of being soluble, it's going to be the opposite. And this would be a insoluble here in water. Taking a look at calcium and chloride, once again, I may not be able to find both of those on there, but we can find chloride. And chloride is, again, soluble in everything except for the 3 we just talked about, silver, lead, or mercury. And in this case, we don't have silver, lead, or mercury. We got calcium, which means that this guy would be aqueous, if I get that written, and it would be soluble. Lead may not be there, but we can find nitrate. And once again, nitrate was one of those ones that's soluble in everything, which is right there, nitrate. No exceptions. So it's going to be soluble in everything. So we would expect this to be aqueous and be soluble. And lastly, again, may not be able to find lead, but it is sulfate. So we take a look at sulfate, which is right here. Sulfate is soluble in everything except for these guys here. And I believe Who do we have on that? We had, I forgot, lead. That's who we had. And lead is right there at the end. And we have lead too. So instead of it being soluble, because it's one of the exceptions, it will be the opposite, and it would be insoluble in this case. And we would expect it to be insoluble. Any questions on how to use the rules? Yeah. I'm going to say you should know how to use them if they maybe are provided for you. No. Other questions? Okay. All right, we're going to lay it up for right now.